Good evening, everybody. Welcome to tonight's edition of the Triangle Area SQL Server Users Group's Business Intelligence and Data Science meeting. This is our first BI and DS meeting of the year. Glad to have you in here. And topic for tonight is getting beyond the basics with Azure Machine Learning. As always, welcome Twitch chat. If you have any questions, thoughts about this, please do drop them in chat. I'll be able to see it right in front of me along the way and answer questions live in real time. In the meantime, let's get started with the presentation. So, my name is Kevin Feasel. You may already know me. I run the Triangle Area SQL Server Users Group, by which I mean I delegate out all the important work and get to be the figurehead at the top. So it's good to be the king. I run an independent consultancy where I work on data science, machine learning, SQL Server, F#. Basically, if it's data platform related, talk to me about it. Also have Curated SQL. The idea is Curated SQL is every day I try to find and link to 5 to 10 interesting resources on topics all across the data platform space. So that's curatedsql.com. And unrelated to this, I have a book that came out from A-Press in the end of 2022. It was called Finding Ghosts in Your Data, and it is all about outlier detection. So that's in Python. If you're interested, there's a link, and I can give you a link to the slides right here. So let's copy that and drop it in chat in real time. Check that out. So, without further ado, let's talk about what we're going to talk about in this talk. So, I will quickly refresh people's knowledge of Azure Machine Learning. My assumption is you've already got some experience. You've tried out Azure ML, maybe you've played with the designer a bit, or you've looked at AutoML. So we're not going to have a basics talk. Now, if you have not worked with Azure ML before, that's still fine. I will give you the 10,000-foot overview, and then we'll dive in a bit. Specifically, what we're going to dive into is code-first programming in Azure ML. A lot of people will start with working with the Azure ML Designer, which is a drag-and-drop interface for performing these sorts of model training exercises. But it's not the only way, and it's probably not the best way. I do recommend learning about the code-first mechanisms because there's a bit more power involved to it, a lot more power, really. We'll discuss the ideas of model registration, of ML flow, and Azure ML's analog to it. Also, I'm going to spend some time talking about pipelines, machine learning pipelines, which is the operating mechanism that Azure ML uses for its process. And finally, I will talk about the reasons behind why ML ops becomes important, machine learning operations becomes important. But we won't dive into that topic because I have an entire talk on it. Also, by the way, if you go to that link, I've created a series of YouTube videos where I drill into basically 3 talks that I deliver. One of them is on getting started with Azure ML, then there's this talk, and then there's practical ML ops with GitHub and Azure ML. So what I'm going to cover is the presentation version of this, but if you want something that's a little bit more bite-sized chunks, I have like a 12 video or 13 video series on Azure ML that drives into these topics as well. So you can check that out if you want. It's on the YouTube channel. The link is the same link as what I gave you before. There will be a link to those videos. So what we're going to do in brief, we are going to take a look at an Azure ML notebook. I'll show you how you can work with notebooks in Azure Machine Learning. We'll analyze a data set. This is a real-life data set. I'll talk a little more about it as we get there. Then we're going to work with some Python code. We're going to build training pipelines, train a model. We're going to perform scoring. Specifically, we'll create a batch scoring mechanism and generate predictions for a whole bunch of possible records and see what the outcomes look like. We're going to see how these things run in Azure Machine Learning and off of the compute that's available in the cloud. And you'll see how you can kick these off from the command line from your own local machines. So that's the idea. That's what we're going to cover. There's a good amount built in here. If you have questions along the way, please do ask them in chat. But first, let's do a brief primer on Azure ML. Maybe a quick reminder for people who are familiar with it and an introduction for people who are not. So Azure Machine Learning, this is Microsoft's primary offer for machine learning in the cloud. And it's been around for nearly a decade at this point, and it's changed a lot over that decade. It is still changing today with the focus on OpenAI and generative AI. We're not really going to touch those topics in this talk. I may develop something in the future about that, but we're going to focus on more of the classic machine learning techniques. So there are several components that make up Azure Machine Learning, and I've got a big list of them here. Let's talk about each one of them in turn. The first is data stores. Now, these are connections where your data lives, and you can see that there are a few of these, and they are pretty much all Azure resources. So we've got Azure Blob Storage and File Share. We've got Data Lake Storage. Gen 1, don't use Gen 1. If you have Gen 1, okay, you may have to deal with it, but Gen 2, very nice. Gen 1, not so nice. Azure SQL Database, Azure Postgres Database, Azure MySQL. So we have databases for SQL Server, Postgres, and MySQL. We have blob and file storage and data lake storage. So all of these are Azure data stores. And the, I'm bouncing around like Max Headroom here. So data sets. This contains the data that we use to train models. Basically, this is your actual file or your table location where the data lives. Compute instances are virtual machines. We host those. They are VMs running in Azure. They have a number of data science and machine learning libraries pre-installed. Think of these as your data scientist VMs that you can spin them up, let each data scientist work on their own processes individually, and when you need to get rid of them, you can just delete it, create a new one. So these definitely fit the cattle, not pets mentality of this is not a virtual machine that you customize and live with for 5 years. This is one that, I messed something up. That's cool. I'll delete it, create a new one, and it's already there. So you use these for remote development, and you can customize what's on here. You can install new packages, keep them up to date, that sort of thing. Compute clusters, meanwhile, are combinations of servers, one or more servers that you use for training or for scoring. Basically, you spin this thing up when it's time to perform training, and I need something more powerful than a single machine. I can have many machines working on a process at the same time. How many? Well, first question is, how much money do you have? Second question is, can you scale that process out? Some processes, like scoring, you can usually scale out really well. Other processes, like training, you may or may not be able to scale it appropriately. Kind of depends on the specifics of the operation that you're running. But one of the nice things about compute clusters is you can have some big iron here, and once your process is done, once you're done scoring, they shut off automatically. So you're not charged constantly for having these things running. Compute instances, you're charged for however long this thing is on. And if you don't have a schedule to turn it off at night or something to turn it off after so many minutes of non-use, this could run forever. Compute clusters by default will shut themselves off once you're done with your training or your scoring operation. The Azure ML Designer, this allows you to train and score using a drag and drop interface. It's like SQL Server Integration Services or Informatica or tools like that, Apache NiFi, where you can drag and drop things, you connect things with arrows, and it kind of leads you to your trained model. This is okay. This is certainly fine for getting used to Azure ML, for learning a little bit about the data science process or the machine learning process, and getting a feeling for what you can do. However, it's pretty limiting. And so we want to move beyond this designer. Now, we do have these notions in Azure Machine Learning of experiments and runs, and we are going to keep those as we go to a code-first solution. Experiments allow you to try things out in sort of a controlled manner. So each experiment has 0 or more runs associated with it. And a run is tracked separately in the experiment. So you could think of this as, I'm going to try training a model using these parameters. And so you feed them in, you train the model, you see how it works, and you say, it was okay, but what if I changed this parameter from 12 to 24? And then you can have another run. So these runs live under an experiment, and the experiment is just a logical container where you can say, this is training my model. And so you have different versions of the model that you're training. You're trying things out. You can compare runs within an experiment and get a feeling for which operation worked out best. So I'm talking about this at a really high level. We'll see a little bit more how experiments and runs work in practice, but that's the concept behind it. Experiments are a logical container. Runs are the individual actions that have occurred under the aegis of that logical container. Now, the primary purpose of an experiment, of having these runs, is really we want to train a model. We want to have a model that we've trained that will be available that we could score off of. So there is a tab dedicated to models. Well, as I mentioned, we also want to perform this level of scoring. And once you have a trained model, you can expose it as an API endpoint for scoring new data. Exposing this as an API endpoint, you could have Azure Kubernetes service or Azure container instances and have it be a web interface. Or you can have a batch endpoint where you say, it's not necessarily that I'm going to call a HTTPS endpoint using REST. Instead, I may feed a data set in and say, hey, perform scoring on this data set. And it'll take that data set, process it, write out some files, and say, okay, I finished. You can grab the files here and see your results. So online endpoints versus batch endpoints. And by the way, Azure Machine Learning calls the first one real-time endpoints. I call them online endpoints because they're really online. They're not real-time. As anybody who has ever had to work with Azure ML endpoints, if your response time is in the hundreds of milliseconds, you're not real-time. But that's a rant for another day. It's a rant I've done many times before and will do many times again because it just sticks in my craw. Inference clusters are a way that we can host endpoints for either real-time or batch scoring. So this is, say, I've got my own Azure Kubernetes service cluster, and I have it available. I want to perform scoring off of that. I don't want to use the Azure ML compute cluster that spins up and then goes away afterwards. Maybe I have a more permanent cluster for this. That would be an inference cluster. And then attached compute, by the way, I don't have a slide for it, but the idea of attached compute is, oh, I'm integrating with Databricks, or I have my own solutions here, maybe a data science virtual machine that I want to attach here, and I want to be able to run off of it instead of a compute instance or a compute cluster. So that's kind of the 10,000-foot overview of what's in the Azure Machine Learning space. And that way, if you're not too familiar with this whole concept, you at least have some idea as we start drilling into the code. So next up, we're going to talk a little bit about code-first programming. So if you do have any questions, feel free to drop them in chat, and I will answer as we go along. So okay, thinking in code. And I suppose I should probably put myself up at the top here so that you can read the slide. It's amazing that way. The designer, that Azure Machine Learning designer, it is okay. It works well enough for learning the basics. You can build a practical model. You can deploy a practical model. And in some cases, that can be enough for a company. And that's cool. If that's all you need, wonderful. But what you usually find is you start getting into it and you say, I'd like to maybe go a little bit off the beaten path. Maybe I want to incorporate some other algorithm, or I want to perform some operation that is very painful to do in drag and drop. Like I want to compare 20 different model types and see which of these works out the best. Very painful when you drag and drop. Instead, we're typically going to want to write some code. And there are two mechanisms that Azure Machine Learning has when it comes to writing and executing code. And we're going to cover both of these in turn. The first one is we can write code within Jupyter Notebooks. The second one is we can execute code from a machine using Visual Studio Code. Now, I'm going to very quickly go over here to my Azure Machine Learning workspace because I was bad before this and forgot to turn on my compute. So I'm going to start up this compute, assuming that I can. Uh-oh. Refresh, please. There we go. So I'm going to start this thing up. It takes 5 minutes or so. That's why I'm starting it now. And by the way, you can see that I have an idle shutdown of 1 hour. I also actually have a schedule that this thing will shut off after a certain time, basically 3 a.m. UTC. So right now it'd be about 11 p.m. Eastern time. And that way, even if I forget to turn this off after the talk, it'll shut itself off after either 1 hour or 3 a.m. UTC, depending. Okay. Executing code with Jupyter Notebooks, that is one thing we are going to cover. The other is executing code from a machine. So instead of having a notebook, we're actually just going to have Python scripts, and we'll run that using Visual Studio Code. Azure ML does have support for Jupyter Notebooks. And let's make myself big again. These will execute on compute instances. It'll be in the standard IPyNB format, and there is a pretty decent web interface for this. And if you're really comfortable working in the Jupyter Notebook space and you hate the Azure ML interface, you can actually use Jupyter Web and get that classic Jupyter Notebook feel. So we have the support for Jupyter Notebooks. They do run on compute instances, and there is an SDK. This SDK is the Python SDK v2. Importantly, there is a v1 SDK. That v1 SDK has not been deprecated. You could still write code using it, but the v2 SDK has a lot of new stuff that v1 will not get. v2 will allow you to work with the different constructs in Azure ML, like data stores, data sets, environments, runs. And if you're using some other language, you want to write R code, I appreciate that. You want to write C# or F# code, Java code, there is no SDK for this. Instead, you can use the Azure CLI v2. So the Azure CLI is AZ CLI, and there is an ML extension to AZ CLI, which allows you to perform the different operations on a machine learning workspace that the SDK covers. So technically, there's feature compatibility between these, which means that when you're running the Python SDK, the calls that it's making behind the scenes would actually be the same calls that you would make from R running the CLI. So it's not that crazy. If you really prefer R to Python like I do, you can do all of this in R. Now, we will demonstrate in Python using the Python SDK because that's just become the norm. But I did want to call that out for those folks who do prefer R and do want to use Azure ML. I've given you two options. When do we use which option? Well, I would recommend using notebooks for exploratory data analysis. You're playing around with the data sets, you're trying to learn a little bit about functionality. Maybe you want to learn how the Azure Machine Learning operations work and do some rapid code development. This is not production quality code. It's not intended to be. And it's intended to get answers quickly instead. So you're trying things out. I recommend notebooks. They're an easy way to get started. There's not a lot of rigmarole that you need to worry about. Many things are just built in kind of behind the scenes for you. But when it's time to write that production code, I do recommend using the SDK or the CLI to build out production level code. There is a lot more ceremony involved, and we'll talk in some detail about that ceremony. But that said, it is a lot easier to deploy, automate, and log results from code scripts rather than notebooks. Notebooks, really good if you're performing manual operations. Deployed code, really good if you don't want to wake up at 3 a.m. to run this notebook because I don't like doing that. So I can easily schedule this to run versus a notebook, which is a little bit trickier to work with. All right, let us look at our first demo. And it looks like our compute instance is running, so life is good. Let me talk a little bit about our data set first of all. So our data set is Chicago parking tickets. This is originating from a database that Daniel Hutmacher put together. And let me drop a link to this in chat because I appreciate all the work that Daniel has done on building out this data set. This is real life parking tickets from the city of Chicago over about a 20-year period. And I'll get to your question in just a moment, Rick. But I do want to drop the link to Daniel's database because, again, it's really good. Let me see if I can find it. So while I'm digging this up, I will talk to Rick's question. And the question was, can you explain again how you can use R or other languages because of the Python CLI? If this is nonsensical, please ignore. It is not nonsense. However, there's a minor amount of confusion there because there's a Python-specific SDK, a Python software development kit. This is a package you can install using pip and will allow you to import modules and classes from for this Azure ML. For every other language, we actually use the AZ CLI, the Azure CLI. The Azure CLI has an extension for Azure ML, and you would be able to make outside calls. Basically, it would be run this executable, AZ CLI or ML, whatever. So if I wanted to train a model against this remote data set using this compute instance in the R programming language, then I would need to make a call out, a shell call out to AZ CLI and tell it run this ML job. So it would not use the Python SDK. It would use the Azure CLI. The Azure CLI and the Python SDK have the same set of functionality, so you don't lose anything with one language versus the other. But there is no R-specific SDK or .NET SDK or Java SDK. For everybody else, you're using the command line interface that Azure provides. So that's the idea. And the link to Daniel's database, I've dropped it in here. It is roughly 20 million or so total parking tickets over this time frame. I think it's like 18.5 million. I grabbed about 1 million of them for this operation. So I have in here Chicago parking tickets folder. This is the one that I was looking for. And within, I've got a file that has roughly 1 million rows in here. And maybe we'll find in a moment if it shows me the set of assets that are in this folder. But maybe it's not going to show me, and I can deal with that. Oh, there we go. All right, so we've got one file. It is, what is that, 128 megabytes of text data. So it was comma delimited data, and it has quite a few attributes to it. We're not going to dive into that yet. I'll talk a little bit about the attributes as we go in further, but just to give you the feeling, we've got this folder, we've got this data set that's already been uploaded. The next thing that I want to do is talk a little about notebooks. Notebooks in Azure Machine Learning are just standard IPython notebooks, so I can create a new notebook pretty easily, and we can see the options that are available. We can also create R scripts or YAML files, text and shell scripts, or just straight up Python scripts. But for notebooks, they are in IPyNB format, and I have one already created in here. So by the way, if you want to grab a copy of this notebook, it is in the repository that I have as a link that I shared already. I can share that URL one more time, and I'll share it again at the end. But it is csmore.info/on/aml in depth. And if I can copy and paste it successfully, then it shows my true skill as an internet user. But basically, this GitHub repository that I've got has a folder in here called Notebook. Inside that is the IPython notebook that we're going to check out right now. So this is taking a quick look at our data analysis. I need to check my compute. My compute is currently serverless Spark compute, which you can use, but we already have our compute running here. So this is 4 cores, 28 gigs of RAM, 56 gigs of disk. Cost me 37 cents to show this off to you. So this is, I will bill you all. Depending on how many viewers there are, I will bill you approximately 1 cent. All right, Chicago parking ticket data analysis. I grabbed 1 million rows randomized from Daniel's Chicago parking tickets database. And then I added a new column called payment is outstanding. The idea of what we're going to do in this is figure out people who got parking tickets. Did they ever pay them off or not? Or was the ticket dropped? Basically, does this person still owe money to the city of Chicago? And that's going to be the question that we'll ask. We're going to do a couple of things in here from azureml.core. So this is using the Python SDK. And azureml.core, we're going to import workspace, data store, and data set. We're also going to import numpy and pandas and load workspace from config. This is a special thing that you get for free when you're working with notebooks within Azure ML. From config essentially says, I'm looking for a file called .azureml/config.json. Inside of there, it's going to have some details. It's going to have your subscription ID. It'll have the workspace name. It'll have the resource group name. I'm not going to show that to you because it does have my subscription ID in it, and I'd prefer not to have that in Twitch land. But this means I don't have to encode anything in here to say, oh, here's my workspace that we can access. I can instead just have that be in a config file, and I don't have to check that config file into GitHub. So nobody has the details for my particular workspace. Then I'm going to get a data set by name. It's going to be called Chicago Parking Tickets, and we're going to convert it to a pandas data frame. So it'll take me a moment to run this. And I want to also kick it off. We can see that I've run this before. So in case there is some failure along the way, we'll at least get results. Taking a few moments to grab the data set and run, wake up the server, got to do its thing. Failed to extract subscription information. Well, that's interesting. I think it's going to cause problems today, and I may need to give it some sass. Well, maybe not. Okay. All right. 1 million rows. We're good. It just wanted to complain a little bit. It's okay. We all want to complain sometimes. So let's look at the top few rows of the data frame, and we can see that there are quite a few columns. Kind of saw that when I looked at the text file, but this gives us a better feeling. When was the ticket issued? Which community in Chicago was it? Sector and side. There's a hardship index and some other attributes. These are attributes that Daniel added on. So hardship index basically ties in things like the per capita income of the area, the percentage of people in the area who are unemployed, who don't have a diploma, the percentage of households below the poverty level, and the hardship index is a calculation that agglomerates those factors and some other stuff. So we can see, are people more likely to pay a parking ticket if they're in one particular type of neighborhood versus another? We can see the ward that they're in, the neighborhood, the tract, zip code, the police district. There's plate type, which is something like this is a passenger vehicle, which by the way, all of these are, or it's a truck, it's a police vehicle. There are several other types of plates, temporary tags, etc. The state in which the plate was issued, which can also be if it's out of country, like it's New Brunswick in Canada. Unit ID, violation ID. So this is, violation ID is sort of giving you an idea of what exactly the issue was. You were blocking the box, you were parked in a particular spot that you shouldn't be, etc. And payment is outstanding. So this first ticket, this person got it 20 some years ago, never paid that ticket. For some of the other ones, the reason payment may be outstanding is 0 is either they paid the ticket or a judge dropped the ticket. So basically, the question is, do you still own or do you still owe the city money? This person, yes. These people, no. But we have a whole mixture of different types of data that we would want to work with. And just to give you an idea of police districts, here's the unique set of police districts. We do have some missing police districts. So we do have some not a number. Now, it is saved as a decimal, but we can see police district seems to be an integer. I mean, there's nothing after the decimal for any of these. So The reason that it's showing up as 15 dot 6 dot is because pandas, if you have not a number, will automatically convert to a float instead of integer types. So if we didn't have any missing values, we would get integers instead. And doing this per data type. So for each one of these columns, how many in this series do we have for issued date? 914,000 unique issued dates. And we can see that the issued date is actually a date and time. So it may be good down to the minute. But what that's saying is, yeah, there are some places where you had more than one ticket entered the same minute. 77 communities, 13 sectors, 9 sides. We can see that some of these, they feel like they are more categorical data. The fact that there's 13 sectors and 9 sides over a million rows, or that there are 22 police districts, maybe that's getting categorical or not, wards and neighborhoods. So a lot of these feel like they're more categorical, that they're more of, let me select this from a drop-down menu versus free-form text entry. And outside of tracked, we can, and also obviously issued to date, there aren't that many cases where we have data in this set that really feels like it is free-form entry instead of being categorical. Now, the per capita income, percent unemployed, and without diploma, without poverty, or below poverty level, these types of things, these are features off of the community. So as a result, we're going to have only a small number of values, even though these aren't really categorical. These are fractions, these are percentages or numeric features that just apply at the community level. And that's why we have a small number of those records. Now, for issue date, as I mentioned, it's almost entirely unique. And as a result, we probably don't want to try to work with the issue date itself. We may want to work with maybe broken it down by year, month, day. So we have the year, we have the month, we have the day. Maybe we even want to split out date and time so we can check, are there more tickets in the morning, late morning, afternoon, drive time, or late at night? And do those tickets get paid at the same levels? So if you get a parking ticket at 3 a.m., are you more or less likely to pay it than a person who gets it at 3 p.m.? Is there a difference? I don't know, maybe. And for license plate, we can see that there are actually quite a few rows in here. Obviously, Illinois is the most common state. 90-some% of our parking tickets have Illinois tags. Makes sense. And then Indiana, Michigan, Wisconsin, all right, neighboring states. And then Iowa, Ohio, close enough states. Then we get Texas, California, Florida, probably people who moved to Illinois. And then you go further down, and you start seeing ZZ. We start seeing some things that are DC, New Brunswick, NB. So AB, Alberta, QU, Quebec. 37 people with Hawaii tags. It costs a lot of money to ship a car from Hawaii to the States, to the mainland. But, 37 people apparently did it. And so on. So looking at this, we can see, all right, the vast majority of people are Illinois, but we might ask the question, do people who have out-of-state tags, are they less likely to pay that ticket? If you came in from Quebec and you don't plan to come back to Illinois, are you going to pay that ticket if you're a Canadian citizen? I don't know, maybe not. So we might want to dig into that some. Plate types, passenger, truck, temporary tags, and there are quite a few other like taxis and livery services. For many of these, there aren't too many records. Like if I've only got 10, 20 rows out of a million in this sample, probably not that important. A and B. So there are 15 tickets written on ambulances, etc. If I look at payment as outstanding and I say, hey, what does it look like for people who have a payment that is due versus people who don't have a payment that is due? Perhaps if I just take a brief look, I might see some vast difference, that the people who make the payments live in different areas or have different per capita incomes in their areas, or that they drive passenger vehicles in the state versus trucks out of state or something else. One other thing that we can do is a correlation analysis. So again, we're still just doing exploratory data analysis, trying to learn a little more about this data set. And if I do a correlation, what this correlation does, df.core, is it is going to perform, if I remember right, it's Pearson correlation only for numeric features. And what we get is a matrix that shows us what is the relationship of hardship index to various other things. So we can see, looking specifically at hardship index and some of these other features, there's very high correlation. Yeah, there's a negative correlation, very strong negative correlation with per capita income, and very strong positive correlation with the rest of these. Well, what that tells us is that if I include hardship index and the rest of these features, that I may have some level of difficulty assigning a particular weight to hardship index versus these other features, because there's a huge amount of overlap between them. So it's hard to assign, well, this is because of the hardship index instead of the percentage unemployed. The real important one that I'm looking at is payment is outstanding, because this is the thing that we want to predict. We want to try to predict, given some various inputs, what's the likelihood that the person will actually pay their ticket? And as we scroll across, we can see everything is like 0.13, negative 0.12. There's nothing in here that says, oh yeah, this feature will absolutely tell you that the person's going to pay or not. And that makes a challenging problem. You know, it's a tough test for us, but I think it's also very realistic that if we knew police district guaranteed that you were going to pay your ticket or not, then this would be a pretty boring analysis. But we don't know any of that. All we know is that there seem to be a lot of very slight correlations between many of these features. So nothing really correlates well with payment is outstanding up front. I can also split this out into year, month, and we can see maybe changes over time. So year and month are down here, payment is outstanding over here. And if I look at the payment is outstanding with year, it looks like there is a negative correlation with year. What that means is, over time, the older the ticket is, the less likely someone's going to pay it. Basically, if you're going to pay a ticket, you're usually going to either pay it quickly or have a lawyer try to get it dropped in court within that year. If you have a ticket that's 12 years old, the likelihood that you're going to pay it in year 13 is pretty low. Like, you've already said, I'm not paying this ticket. You've already had it lapse for 12 years. You're already probably have a warrant out for you in the state. What's another year? Especially if you live out of country. So we can see there's some idea behind why this could be negative, but it's a minor negative. Also, month, no real correlation. So it seems like month is probably not going to be relevant for us. So, all right, final cleanup. Are there any columns with not a number? Yeah, it looks like there are a few of them. Tracked, as well as police district, plate type, and license plate state. So it seems like we've got some missing plates, some missing police districts, some missing tracts. We may want to clean those up along the way. So wrapping this up, our plan of action, see if we can find and replace those missing values for police district. We want to create some features for the year, the time block, the license plate origin, and vehicle type. Group things together instead of having every state individual, in some cases where you've only got 1 or 2 or 10 entries. Remove hardship index because it's really highly correlated with several other features. And remove census tract because there are missing values, and also it ties in really well with neighborhood and ward. So it's probably not going to give us much more of a benefit that we would not get from neighborhood or ward. And encode these categorical features that we see. This is what we can do with a notebook. It's all pretty straightforward analysis. We haven't built a model. We haven't done anything really fancy yet, but I've been able to run this. It's running on my compute instance instead of running on premises in my own personal compute. So if I've got a low quality laptop, I can run this, have all the code running, and all I need is a web browser, which is what I've got open here. All right. That said, if you do want to run code locally, I do recommend using Visual Studio Code. Visual Studio Code has a lot of support built in for Azure Machine Learning using the Azure Machine Learning extension. So that's an extension that you can install in VS Code. Works really well for the task. It'll give you a direct interface to your AML workspace and then lets you turn your local machine into a compute instance if you have Docker installed. So I can run things locally if I do have that GPU that I want to mess with, or if I do have a powerful machine that I can train off of, while still getting the benefits of the machine learning workspace, of having my data stored in the cloud, by having some of the mechanisms available to me for model registration that we'll talk about later on. Actually, we'll talk about it right now, it seems. While I take a bit of a drink. Anybody have any questions? Assuming no questions. Of course, people could be typing furiously right now and trying to put in their questions, but we'll talk about MLflow while people type. MLflow is an open source product that came out of Databricks, and the idea is we're going to manage machine learning development lifecycle. So that is, MLflow allows data scientists to train models, register those models, deploy them out to a web server, and manage updating the models. It is a central model registry that has several components built in. It makes its use mostly in Databricks, but it does go well beyond that. You can install MLflow for your own model development. You can install that all, run locally, not ever touch cloud services. I find it to be a really helpful product. And Azure Machine Learning has several parallels that make it quite easy if you're working with MLflow to integrate. Now, MLflow is made up of 4 separate products, and those 4 products are going to help us manage ML development. So the first one is MLflow tracking. The idea of this is we're going to let scientists work with experiments. So for every run in an experiment, we can log parameters, we can log which libraries we used, what versions of libraries we used. We can track the evaluation metrics. How well did this thing perform in testing? And generate some output files when we're training our machine learning models. So MLflow tracking keeps track of those metrics, those outputs, those artifacts, lets us audit our processes for model training. MLflow projects allow us to package up our code that we can consistently deploy and hopefully reproduce our results. There are a few different ways of packaging these things out. You can build a Conda package, you can build a Docker image, or you can deploy this directly onto a system. MLflow models are a consistent standardized format for packaging models. So this is a little different from packages. Packages is how do I push stuff out to servers? Models is how do I store the information about a model in a way that's fairly consistent? Because I could have, for Python, I might have a pickle file that has my trained model. I could have H5 files. I could have tensor packages, tensor files. I can have a series of different types of file depending on which model I'm using. And MLflow has some support for a variety of these things. So if I have a scikit-learn trained model or something from PyTorch or TensorFlow or an Onyx model, it's going to take all of those, serialize the outputs in a way that we can access it later on. Regardless of if I used TensorFlow to create this, I can then pull the model out of storage and score against it. So question in chat, any standardization with the varying values? And I'm not quite sure what you mean by that question, if it's regarding experiments and runs or something else. But if it comes down to, if the question is, hey, are there standard sets of parameters that get logged for MLflow tracking? The short answer is not necessarily. It's whatever you would create for yourself. Now, each library that you use, like if you use scikit-learn, there are going to be several metrics that they're going to be biased toward because they're easy to recreate in scikit-learn, like root mean squared error or mean absolute error, median absolute error, or R squared or something else, depending on the type of model you're training, the type of process you're running through. And you may find, oh, this is a lot easier than developing my own custom metrics. So we may see more of, I'm doing regression, so I'll see root mean squared error and I'll see R squared because those are easy to create. But there's nothing that says your experiment must have these particular outputs, these particular logged values. So that would be entirely whatever you're creating when you write these logs. And if that's not your question, please feel free to add a supplement and we can talk about it. So the fourth thing, we've got our models stored, we've got our projects, we've got our experiments and runs. Well, we also need a way to register these models. Basically, I hinted at this when I said, hey, we're storing our models. The model registry is our way of keeping track of models, especially over time, different versions of a model. Like, we're going to build a model for Chicago parking tickets. Well, I'm going to have another version of that later on. Maybe I've got different techniques that I want to use, or I've got new trained data and I need to rebuild this model, retrain it. We can have different versions of the Chicago parking tickets model. And then I'll have a different thing for analyzing some other data set. So with these registered models, operations people can easily deploy the model out to a web service and expose it using a REST API. Or you can use batch inference. Both of those are possible. Those are the four main features, the four main tools within MLflow. Azure ML has pretty much almost all of that functionality just built in. So if you're already using MLflow, it also turns out you've got that server set up, your team has spent time learning about MLflow, you're very comfortable with it. Cool. Use it to store your Azure ML models as well. That'll work just fine. But the model registration capabilities in Azure ML, they were intentionally designed to mimic what's in MLflow. So if you're familiar with the syntax in one space, it's pretty easy to switch over to the other. Like MLflow tracking, Azure ML has experiments of its own. It has runs of its own. And the concepts are very similar to one another. When it comes to a given run, we can track the details of metrics that we've logged. And this is an example of what I mentioned. This is a root mean squared error over the course of a few different inputs for people. This was a prior demo that I gave. The data itself is not relevant, but I can track a whole bunch of different metrics this way. I can store basically whatever I want in the metrics for this experiment, and we'll be able to read those later on. I can also review the actual files. Like, this is the file that was used for training for this particular operation. And that can be nice if I want to figure out, why did this happen? I thought my Python script that I've checked in a source control looks like this. And then I can go check to see what was the Python script used to train this originally and say, oh, weird, it picked up the old version of this script, and then diagnose why that happened. And it could be, oh, somebody kicked off the training job before I actually checked in the new version of the script. So kind of helps you diagnose those sorts of problems. And one other thing I'll call out is for outputs, we can also upload images. So we can generate images as well within our code and say, here's a heat map of the correlations between different features. And I can write that out as an image and then be able to view that image later on. So if I'm trying different sets of hyperparameters, I might track each one and have the whatever parameters I need to log for those different runs of the experiment and compare and contrast them. For projects, well, if you use MLflow projects and you're packaging up code, there's an equivalent to, I'll just execute that on Azure ML Compute. It's not exactly the same thing, but in Azure ML, we do have this notion of pipelines, and we do have the notion of our code that we're executing is built into Docker images. So we are Dockerizing our code and deploying it out, these container images out. The model registry, there is a model registry in Azure ML, and it is, again, very similar to the one that you would see for MLflow. We can register, we can store these models in here, we can see the versions of them and track information. Each model will contain whatever stored artifacts we need. Like if we do need H5 weights for a particular job, if we do need something other than just the sheer pickled model, we can store those as well. Models also can contain information about the data sets that we use to train them. We can see here was the data set that it was used to train on, and here's the version of the data set, because we know data sets can change over time. And if I have a snapshot from August of 2023 and another snapshot from February of 2024, well, the trained models may be very different. And so I want to see on which data set was this model trained. Once we have that model in place, it becomes pretty easy for an operations team to deploy it. In the Models tab, you select the model that you want, you select the Deploy dropdown, and we have two options here. We can deploy to a real-time endpoint or to a web service. And if we're deploying to our service, then that's going to spin up something where we can run an Azure Kubernetes service or Azure Container Instances. We can also, through the Endpoints tab, create batch inference, batch endpoints, where here's a file, score this entire file, instead of I'm going to make a web call and get back my data. So that's the high level on MLflow. And I wanted to walk through all of this. I know there's a lot of preface to what we're talking about, because when we get into the code, a lot of this will come back to haunt us. So let's talk ML pipelines. Azure ML is built around this idea of pipelines. With ML pipelines, we're going to perform data cleansing, transformation, model training, model scoring, model evaluation. Whatever we need to do, there are going to be different steps in the pipeline, and we'll operate from step to step, sending our output of the prior step becomes the input of the next step. That allows us to do our data transformation and training as part of an inference pipeline as well. So when it comes time to generate predictions, I could do that data cleansing and transformation the same way that I did for our training process in the inference process. When you're using the designer to train models in Azure ML, what we're actually doing behind the scenes is we're creating pipelines. Each one of these blocks is actually an element in an Azure ML pipeline. So here's one that says select columns in data set, clean missing data, normalize data. All of these things, these are different pipeline elements. And that's what our flow is actually showing us. So why might we want to use pipelines? And there are several reasons for this. One of them is this lets us script our code out for source control. I can create a series of different scripts. They are fairly small scripts, and you can analyze each one of them. We could do code reviews on them individually. Different instances, you could control deployment. So I want to run data cleansing and transformation on a cheap server because we're not doing a lot of work with it. But I want to run model training on a server that has a GPU, which is a lot more expensive. That means we get heterogeneous compute. We can reuse components between pipelines. So if I have a data transformation process that I use in 3 different models, I can actually create a library, make that component available, bring that component in those 3 separate processes, and use the same component 3 times instead of copy pasting code across 3 projects. We can collaborate with other people. Maybe one person is working on data cleansing, one person is working on model training, one person is working on the scoring and deployment. So we can divvy out that work across the board. And when it comes to pipeline steps, we are going to need Python installed and the Azure ML SDK v2, or like I mentioned, the AZ CLI with the Azure ML extension for any other language. I am just going to use the Anaconda distribution of Python. You don't need Anaconda for this, but Anaconda has many of the things that we need up front, so I'm just going to install it. All right. Did that thing again where I hide myself, and it's time to look at the code. So now we're going to dig into our demo. And for that, I am in Visual Studio Code, and I may end up just going and hiding myself depending on how it looks. All right. I have in here .azureml config.json. Not going to open it up, but in here, this is just a simple JSON file that has my subscription ID, it has my resource group name, and it has my workspace name. I also have the notebook that we looked at earlier. I've got a series of scripts, and we're going to talk about the training process first, and then we'll look at the scoring process. So let's talk about training. And actually, I'll move that up here. We're importing several libraries. Unless something is very important, I won't mention it up here for the sake of time. What is important? Azure.ai.ml. This is the SDK v2. If you see code examples that don't reference Azure.ai.ml, they are using SDK v1. So as an example, I have azureml.core. This actually was a reference to SDK v1. This is SDK v2. And I do recommend if you're writing code, use the azure.ai.ml namespace and library. If you're interested in learning more, I do have some notes in the README on this. There we go. That will tell you, okay, here's the Anaconda distribution, Azure CLI, pip packages that you'll want to install, Azure AIML, and Azure Identity. So I kind of walk you through some of the process of what you're going to need to do. And while I'm thinking about it, I should probably open up an Anaconda prompt. I should probably go to the appropriate directory. Beyond the basics. There we go. And let me bring that over here. So let's log into Azure. I'm logging in as me. Hooray, I've logged in as Azure. So I can close that window and cool. So we've logged in. That will become relevant later. And actually, until it becomes relevant, let me move this over here because I don't want to show everything that I've got on there. And come back to these files. Deploy train.py. We're importing quite a few things. And let's talk a little bit about the process. My workspace is CS Azure ML. My cluster name is CPU cluster. If I head back to the Azure Machine Learning workspace, we can see that I have a cluster called CPU cluster. It's in compute, compute clusters, CPU cluster. It already exists. In the event that it did not exist, I would, down here in line 38, say, try to get that cluster. And if it already exists, it'll tell me that I have it. Otherwise, it'll create a new compute target that is of type AML. So it's AML compute. It is DS3 v2, which is pretty cheap. It's I want to say something like 17 cents per hour. And we'll have between 0 and 4. 0, I don't want to pay for it if I'm not actively running anything. 4, the maximum number of nodes that I'm going to have at any point in time. And wait 3 minutes after the job finishes, just in case I have something else that I want to kick off. Otherwise, it's going to take a little bit of time to spin this back up. So we have some code in here to create our cluster if it does not already exist. We have also up here my ML client. I get it from config using my Azure CLI credential. That's why I had to run AZ login in the console prompt so that we could get this. Then I'm going to get all my workspaces and based off the workspace name. So I'm going to get whatever is available in CS Azure ML. We're going to try our compute cluster. We're going to look at this config directory and perform data preparation. So if I jump into the config directory, we can see that there are about a half dozen different files in here. And let's look at this first one. Load component feature replace missing values.yaml. So that's this right here. Feature replace missing values.yaml. This is the standard format for Azure Machine Learning config files. It's got a name, which is the name that we're going to reference within our code, a display name, which is what it's going to look like in the Azure Machine Learning space, version, type. I always just leave these as a default. Inputs. We have one or more, well, 0 or more inputs. In this case, we're going to have input data, which is a folder. And then our output is output data, which is a folder. The code itself will be in a folder called scripts that is at the same level as config. So we go up one level and go into the scripts directory. And the environment. The environment is what Docker image do we want to start with to execute our code. And the Docker image I'm going to use is this registries Azure ML environments light GBM version 3.3, and actually the version 2 of this container image. This is called a curated image. This is an environment that Microsoft has put together and just made available to us. We can also create our own custom images, install whatever packages we need to on it, and then build out a Docker container and an image and deploy that and make it available. But I'm just going to use one that Microsoft has built because it has everything that we need. As for commands, simple command, run Python feature replace missing values.py. Well, that's this file right here. Input data is input data. Output data is output data. So we're going to have our inputs, we're going to have our outputs. Now let's check out what's in the Python file, because that's what this command is running. The Python file has a fair amount of code. It's like 50 lines of code. But we can see that the first bit here, this is arg parser, argument parsing, essentially saying, make sure that the inputs are correct. If you don't have input data and you don't have output data, somehow you called this the script incorrectly, we're going to throw an error, basically. Then I'll write out what the paths were for input and output data for diagnostic reasons, and print out the list of directories for input data, because the list of the directory for input data, because I want to make sure that I have the right file or files in there. Then for each file, we're going to read that file. So that's opening this file, and read this as a Panda CSV. Basically create it from CSV, read it in as a data frame. And that's for each file. So if I have 10 files in here, I'm going to have 10 data frames total. And then I'll concatenate all of those data frames. So file list is actually a list of data frames. And then I'll smush them all together into one big data frame called df. After that, I'm going to do the actual work. All that was preparatory. It was logging. It was making sure that the values were right. It was reading through the files in order for me to do my replace missing values. In this case, replacing missing values basically says, if you have a police district that's missing, so NA, fill it with 0. I don't know what the proper police district is. I'm being lazy. In real life, hopefully I have some better information based on values like what is the ward, what is the neighborhood. Maybe I can get the police district from those. And then I'd be able to fill this in with the appropriate answer. But because there weren't that many missing police districts, I just said, make it 0. That's okay. And then we're going to write out our results to the output data folder as replaced missing features.csv. That's our output. It is in a folder written out to CSV file, and that is feature replace missing values. The rest of these features are very similar. We have a configuration that takes an input, writes an output. We have a Python script that does something. Like feature selection, we drop tracked, hardship index, issue date, license plate state, plate type. So drop some columns. Feature engineering, we create some columns. we create the year of issuance because we saw there's a minor negative correlation between issued year and the likelihood of getting a ticket paid. Time based on hour of day. So I decided I'm going to bend this up. I'm going to make this overnight, morning, midday, after work, and evening. And why those specific times? I just figured, well, if you get a ticket during drive time, if you get a ticket the middle of the day or after work hours, or you're out at night, or you're out there late at night, perhaps there would be a differentiation in how people pay those tickets off. The origin, Illinois or out of country or everybody else. So we have in-state, out-of-state, and out-of-country. Plate types, passengers, trucks, temporary tags, or anything else. And so that's our idea of feature engineering. So we're putting all of this stuff together, using these YAML files to explain, here's the actual work that needs to be done. The Python scripts do the work, and then this deploy train is how we tie together the pipeline elements. So I have here load component. Load component comes from Azure.ai.ml, and we send in the source location of that YAML script. And the YAML script does the rest of the work. And we're going to load this component and call it replace missing values. So this returns a function, replace missing values. We're going to load feature engineering, load feature selection, split data, train model, register data. All of these are YAML files. Like split data actually is a little bit different because we take our input data set and we output training and test data sets. The process for splitting the data, I just use scikit-learn's train test split and say, hey, 80% of this will be training data, 20% of it will be test data. With test data, we still have 200,000 rows, so we have a pretty beefy test set at 20%. And I have a fixed state because I wanted to be able to rerun this and get basically the same results. Then train model, register model. So train model, we have many different inputs. We have our training data and our test data, and then we have various hyperparameters that we are going to use. Maximum number of leaf nodes, minimum samples per leaf, maximum depth, the learning rate, number of estimators. So we're using something tree-based, just based off of the inputs. And we get out a model and a test report folder. The training script is a bit more complex, so let's talk about that in a moment. I just want to make mention that this training script is here. It is a little bit more complicated, but let's go back to deploy train first. I've got my different elements, and now let's build a pipeline. So this pipeline, I have a @pipeline attribute tag to indicate this is our pipeline. We've got a name for it and a description. Here's what we're doing. We're going to build a pipeline given some raw data. That raw data will be our Chicago parking tickets data set, the 1 million rows. Then I have different steps. The first step is I need to replace missing values. Well, that came from load component. So we created a function, replace missing values, that takes as its input our raw data that we're feeding in. And that creates step missing value, replace missing values. Then for the next thing, feature engineering. So we're calling feature engineering. Our input data takes from our prior step the output data as the new input. So we go from input of raw data through replace missing values, generate some output, take that output, make it the input of feature engineering, generate some output, make that output the input of feature selection, make that output the input of split data, and so on. So this is how we build our pipeline. It's basically we're taking step by step, feeding the output of the prior step into the next step. It doesn't have to be just that. For train data, we have the output of split data. We actually have two outputs, testing and training data. And then I have some hyperparameters that I have specified here. There are ways in Azure Machine Learning to perform stepwise hyperparameter tuning. So it's called a sweep. We can have choice or uniform. And for choice, that could say, I want a choice, maybe maximum number of leaf nodes could be 32, 64, 128, 256. And so I would have effectively an array of possible values, and I'd pass in that array as a sweep parameter. So we'd have those for each one of these parameters, and what would happen is that we would train on each one of those, or some percentage of the possible combinations, depending on how we set up the sweep operation. For this case, no sweep, just one set, 128 leaf nodes, minimum samples 32, maximum depth 12, learning rate 0.1, number of estimators 100. Why those numbers? They seemed good enough. That's the fancy reasoning behind it. I'm not guaranteeing these are the best values for this particular model, but seemed good enough. Give us a result that we can look at. It's kind of the reasoning behind it. And then register model. So I get the model output and the test report, and I can register those. Let's look at registration before we look at training. For registration, we're going to take in our model, we're going to take in our test report, and we're actually also using MLflow, mlflow.startrun. Azure Machine Learning's model registration process uses the same interface as MLflow. So you can just import MLflow and use the same code that you would use for on-premises MLflow or Databricks MLflow and start a run in Azure ML. It'll work just the same. We can upload files. We can get context of the run. We can work in our workspace. We can load models with mlflow.sklearn or mlflow.pytorch. We can save models into the registry. So here I'm saving the files locally, and then I'm registering the model as Chicago parking tickets code first, and it's using a boosted tree. Spoilers. And then we register the model in the Azure ML model registry. Here is the path for the model. Here's where you're going to find all the artifacts. Here's what I want to call the thing. Here are the results. So I'm tagging, I'm creating tags for each of the results. Like here is the value. Here's the root mean squared error. Here's the R squared or whatever evaluation metrics we're including. And that way we can have those easily show up as tags, not just as metrics that we would have to drill into to find. Finally, our pipeline needs to return something. It's a requirement of a pipeline at Azure ML. So we're going to return a JSON dataset. This JSON object has model and report. So we are going to take that model output and the test report, and we're going to write those back out. So that's our pipeline, build pipeline. We have this prepare pipeline job given a cluster name. Our cluster name, CPU cluster. We're going to create Chicago parking tickets folder if it does not already exist. So we need to grab Chicago parking tickets folder. We've already got to have that in place. And I can go back here. I can check. I have Chicago parking tickets folder. That is the location that has one file with 1 million or so rows, and it's just one uploaded file. So I need to have this in place before I run my code. We're going to load this up as a URI input. I'll just call it raw data. So it's going to be basically our Chicago parking tickets asset, the location of that asset, and then we'll call build pipeline and create a pipeline job. We'll set the compute cluster that we're going to run this off of, and a couple of basic settings. We're going to say you should write out your results to Workplace Blob Store, which is a data store that I've got on here in Azure ML. It's kind of a default data store for Azure Machine Learning. It's a blob storage location where it can write out whatever it wants. In the event that I have already run this before, there we go. Back to where we were. In the event that I've already run this before, I can force rerunning. Basically, if you have run something and you have not changed the input data, you have not changed the code, Azure Machine Learning is smart enough to say, oh, you've already run this. I'm not going to run this again because I'm just going to get the same results. So you can set that to false, and what that'll do, if you haven't changed any of the inputs, it'll just say, you've already done this before, so just use your prior model, and that way you don't have to spend the money on retraining this. But because I want to retrain this, I'm going to set this to true. And then I'll call this train pipeline and return the pipeline job. So down here at the very bottom of the script, this is the actual work that we're doing. Prep job, prepare pipeline job. So it's going to call this function. It's going to call this function. It's going to build all of these functions. It's going to call all this code. It's a whole process. And then we will call ML client, the Azure ML client .jobs.create or update. Here's my job. Put that in the Chicago parking tickets code first experiment. If that experiment does not exist, it will create it for us. And then I have a little print statement that says, hey, go look at the status of the pipeline job. So how do we actually run this thing? And by the way, I haven't forgotten about train model. We will look at that, but I want to kick this off first because it'll take a little bit. How do we actually run this thing? Well, I've got a nice note in here. I have already my Azure ML config JSON, like I mentioned, and I have to be logged into the AZ CLI. So once I'm there, I have my directory. I need to go into pipeline, and we can see deploy train.py. Python deploy train.py. If I have lived a good life, if I've done things correctly, if I've not forgotten anything, which that last one is very possible, well, we're going to be able to see this thing kick off and start running. So it found our config file. That's a good start. And it's going to begin processing. It says, hey, you've already got a cluster, so we're going to use this as is. We have some notes that come up, some warnings that come up. No big deal. They're experimental classes. It's okay. We're not really going to do anything with any of these. But this will run for a little bit. And while that's running, let's talk about what the training process is actually doing. So up here, we have our imports. We are doing a lot of scikit-learn. We're actually doing nothing with Azure ML. This is important because when we kick off this training script, when we're in deploy train.py, or actually, no, sorry, let's talk about trainmodel.yaml. When we're in this environment does not have Azure ML installed. It's just a container registry image that has light GBM and has some Python scripts and packages installed. So it'll have pip set up. You'll be able to install other packages if you need it, but it'll have scikit-learn. It'll have MLflow. It'll have pandas and numpy. All this stuff is available to us, but nothing Azure AI ML. So we're going to work entirely from scikit-learn in this training. We have defined a main function with some arguments. And if I scroll all the way down to the bottom, our script, if we have, if our name is main, then start an MLflow run. We're going to parse our arguments, then call main with those arguments. And once we're done, we're going to end the run and print done. This is because it's a little bit more complicated of a script. I wanted to have a proper main method and break out the parsing of arguments into its own function. So we have a lot of input functions, input arguments that we need to process and make sure that they exist. And assuming that we parse them correctly, we'll go into main and then load all of our data sets from train file list and from test file list. In practice, there's just going to be one file, but I wanted to have this in case maybe we were using a distributed cluster to build out a series of train files and a series of test files, and it writes them all into this folder. So we're going to loop through, pick up all of those files, read them all into CSVs for input data frames for training and test. So we have the train data frame, we have the test data frame, and we have this process data function, taking train data frame and a separate call using the test data frame to build out X and Y. X and Y X is our input features, Y is the output that we're trying to predict. So our features, we have numerical and categorical features, and we have one label column, payment is outstanding. So our numerical features are all of these, our categoricals are all of these. Label column, payment is outstanding, and we're going to say all columns is numerical, categorical, and our label column, which we're going to make it a list so that we have a list equals a list plus a list plus a list. And then we'll create a data frame, pulling in all of those columns. If there are any other columns, I don't care about them. I don't want to worry about it. Then drop any records where the label column is null. I don't remember that there were any. I think everything has a label. Everything has payment is outstanding, but just in case, I don't. This is a supervised regression process, so I don't want to have any cases where I don't know what the answer is. And then I'll print out number of non-null label rows, and we're going to drop the label column from our X, from our input predictors. Y will be just the label column, just our output payment is outstanding. And for categorical, we'll type them as category. For numericals, we'll type them as float. And then I'll return X and Y. So that's the idea of what process data is. It's preparing our data sets so that we can perform analysis on it. Our train model, we have various parameters. You can see the different arguments that we have set up. So max leaf nodes, minimum samples, max depth, learning rate, number of estimators. Our validation, we are going to perform validation using 10% of the data. So really, train 70%, validate 10%, and then test 20%. And the training, I've got a function, train model. So let's take a quick look at what that's doing. We take in our parameters and our training and test data sets. So the input parameters, the feature that we're predicting. The test input parameters, the test feature we're predicting. We are going to make a pipeline, perform some imputation for our categorical variables. I'm going to use mostly one-hot encoding. So one-hot encoding basically says for every collection of inputs, maybe I've got 10 possible values here. Well, for 9 of those values, we're going to create a new column, and it'll just be a simple yes or no. And for the 10th one, if all of the input values are no, we can impute that that one's yes. So the whole idea is that instead of having a category, which is a string, we now have a bunch of numbers, a bunch of ones and zeros, or Booleans, trues and falses. We're going to do that for all categorical features. Then for the rest of these, we're going to impute using the median, meaning if I have a numerical feature that doesn't have a value, I'm just going to set it as the median. And I will also do min-max scaling to normalize stuff out to 0 to 1 range. That way, the per capita income being 3 or 4 orders of magnitude bigger than the poverty level, percentage of people in poverty, won't wreck our results. So everything's normalized on a scale from 0 to 1. And then I'll perform a gradient boosting classification. So think XGBoost. I'll build out a pipeline using my column transformer and my classifier. So yeah, sorry, I'm not doing regression, I'm doing classification. In an earlier example, I tried to do regression on some of this data using the dollar amounts, but I don't include that in this data set. This is just classification of yes or no. Are we in fact going to owe the city money? And if we owe the city money, are we going to ever pay them off? And we're going to fit our model. So given our X and Y training data, we're going to build out our model. By the way, speaking of which, let's see how we're doing here. So it looks like this is in fact running, so that's good news. Let's see if it's really running. To see if it's really running, I'm going to be here in Azure Machine Learning, and I can go into jobs. And inside jobs, I have my different experiments. One of those experiments will be the Chicago parking tickets code first. It's right here. And I can see that I have a training pipeline that is currently running. Now, spoilers, normally takes about an hour for this thing to finish, which means we're not going to see the thing finish, but that's okay. If I drill in, I can see the job that's running in process. And we're at the replace missing values step. And then there's feature engineering, feature selection, split data, train model, register model. All of our steps in our pipeline, we get a fairly nice graphical interface for it. So the status right now here makes it look like this is actually spinning up the cluster. So it's waiting for the cluster to be available before it can run anything. That'll take a few more minutes probably, and then it'll start doing its thing. In the meantime, let's continue talking about our model. So we've got our trained model, our classifier model, and then I'm going to predict, given the test data, what our predictions should be. And then I will create a series of evaluation metrics. Accuracy, F1 score, the F1 micro and macro, precision recall, and the receiver operator curve characteristic area under the curve. I'll write all of those out to results. I'm going to print results, and then I'm going to log those metrics. So this will write it out to the output, to the console, and then it will write everything into MLflow for the experiment, for that particular run of the experiment. And that's what our training process is doing. If I look at a prior run, so now this is blue, this is actually running the step. If I look at a prior run, this one I ran just about a month ago. So hopefully we've still got all the details, all the metrics. We have all of our steps. So, that's good. If I right click on train model, I can view the log and what we get out of this. 800,000 rows. We see our accuracy, F1, etc. This is what we wrote out to the console. But I also have metrics. And my selected metrics, I have analyzing the metrics for the job. Let's select all of them. So I can see them in here. Accuracy, F1 score, F1 macro and micro, precision recall, and area under the curve. What this is saying, hey, it's fairly precise, not great recall. Basically, it's pretty good at telling us that if you do not have a parking ticket, it's pretty good at telling us the people who will pay off their parking tickets. It's not great telling us the people who won't pay off their parking tickets. So that's the top line story of what we're doing here based on how I had precision and recall set up. But inside here, I can see the code that was used to execute this particular operation. So we see all these different scripts. Here's my train script. Here's my split and score and register models. I get all of that stuff here, which means in the event that maybe something broke and I needed to diagnose why, I can check out these individual files. So all of that is available here in the job details. If I go back to the job overview, I can see that it completed. I can see some information, grab report details, and back in the experiments list, if I head up to dashboard view, I can even get some information on multiple runs of this. So, I'll hide the dashboard view for now, but I can see cases where I might want you, and you, and then visualize for some of those and see what it looks like across those sets. I haven't played much with the dashboard view before, haven't really needed to, but there are things that you can do with it that can be pretty interesting. Nonetheless, that's the idea of training. So we're training, we're building out this model, and at the end of the day, what we want to do, we want to register that model. And I mentioned there's this model registry. Well, in the models, I have Chicago parking tickets code first. And you can see I've created this a bunch of times. I'm gonna delete this version, number 11. I'm also going to delete number 10. It'll take a moment to delete these, but once it's processed the delete, let's go into 12. This is version 12, and this version was generated about a month ago. We can see the artifacts. It'll take a moment for this to pop up, trained models. So I've got a pickle file. I've got a conda file that tells here are the different versions of packages that I needed for this. I've got a Python environment YAML file. So I need pip at a certain version, setup tools, and wheel. And I've got a requirements.txt. So there's a few different references that I need in here, and even a ML file. This is what the model registration gave me. I didn't have to specify, here are all of my things that I needed. What I did specify was this code, all the scripts here. So that's what I have. I didn't even really need to specify the requirements.text, which is kind of nice. No endpoints, no jobs, no data. So nothing's really been done with this yet. And let's change that. Let's go into scoring. I know we're running pretty long, so I'm going to breeze through scoring a little bit. I won't go into the same level of detail, but let's kick off the scoring script right now. Oops. Python deploy score.py. What we're going to do is same thing, CS Azure ML using our compute cluster. We're going to load up the compute cluster, make sure that we can access the workspace, and our endpoint will be called Chicago Parking Tickets Batch. And if we have one already, we're going to get it. If we don't have one, we're going to create it. And if I go over here to endpoints, and I select batch endpoints, we're going to see that we actually already have one. So that's good. Then we're going to get the Chicago parking tickets code first model. Now, if I leave this blank, if I delete this bit, it'll grab the latest version. But I'm going to specify I want version 1. Version 1 is the same as all the other versions because I'm using the same seed for training. I'm using the same input data set. They should all be the same or very close to the same. So we're going to grab that version of the model. We're going to build out a deployment. A deployment is basically saying, okay, at this endpoint, this batch endpoint that we're creating, Chicago Parking Tickets Batch, using this model, Chicago Parking Tickets Code First, in some environment. The environment is Azure ML Scikit-learn 1.0 running on Ubuntu 20.04 using Python 3.8. It's an older image, I'll grant you that, but it's a goodie, oldie but goodie. We are going to create 2 instances. You can access up to 2 instances at a time. We're going to allow up to 10 files per batch. So that's what a mini batch is. It's however many files you've got. And output, append all rows to a file called predictions.csv. And we're going to log at info level. So we'll create or update this deployment and then make that the default deployment for this batch endpoint. And after that, here's my data path. It's data. So inside data, I've got a couple of different files. Chicago Parking Tickets 1 and 2. These are just 2 files that have data in the format that we need and do not have payment is outstanding. By the way, if you're using Visual Studio Code and you're saying, wow, I wish my CSVs actually were color-coded so that I could understand what the columns are, this is an extension that is called Rainbow CSV. There we go. Rainbow CSV. This is a really cool extension that colorizes your CSV files. I found it incredibly useful. So we've got 2 files. They're just fairly simple files. This one has 2,200 input rows. This one has 391 rows. No big deal. We just want to perform scoring for those. So we're looking Chicago parking tickets unlabeled. We're going to see, is there a data set in Azure ML already around that? And it turns out there is. Inside here, if I select Explore, there are going to be 2 files. One with 2,200 inputs, one with 391 input rows. We're going to use this data set. We're going to generate off of it. So if I don't have it already, we're going to upload these 2 files to it and process away. We'll invoke our batch endpoint. What this is saying is, hey, take this input data, perform scoring on this endpoint, and generate the results, write them out to a directory. You'll tell me what the directory is, and I'll go look at it later. We'll stream the job and wait for it to finish, and then download the results at the end from score in the local directory. So if I look at this script here, what we've got is it found my config file. I have a cluster, I have an endpoint, I have a deployment. So it's just going to kick this thing off, and we're streaming our run. So that will take a little while as well. If I go back to jobs, we can see our batch job is running. This one normally takes about anywhere from 2 minutes to 10 minutes, but that depends on whether or not the cluster is already up and running. Cluster is running because I'm training right now. So assuming that I've got at least one server available for the cluster to pick up and work off of, then we will be able to see this batch scoring run. Now, it looks like it's probably going to take the 10 minutes. It's probably got to start up a machine because I'm using some of those servers for training, which means we may not see it immediately. But fortunately, I've got an example of one where I have run it. So my batch scoring operation, I can view the log. And we have our output logs. We have job result. It says there are no mini batches. 1 succeeded, 0 failed. That looks pretty good. We have user logs. This was what was written out. It took less than a second, so it seems like didn't take very long to do work. I'm wondering if this one actually did any work. And there are a couple of metrics in here: active node count, failed items, etc. But one mini batch, okay, one mini batch, one node ran, no failed items, progress was complete, processing status, okay. So you might ask, well, all right, this all looks great, but like, where do I get my results? Where's my output for this? Well, a couple of things. One is, as we're running this script, the end of this script, we're downloading a score file to a local location. So in this local directory, I'll get a score file at the end. But let's say I want to go back and look at it later on. I want to see what the result looked like after the fact and understand, well, this file is good and all, but I need something more. And for that, there is a location where all of this gets written out. And I'm trying to remember which file it is that shows you the output location. Because basically, data outputs in here, my score, I can take that data set and access it, and it'll pop up Azure Blob Storage. And inside Azure Blob Storage, you can see, if I zoom in a little bit, we have this Azure ML Blob Store GUID / Azure ML / GUID. You're not going to figure out what these GUIDs are unless you happen to know, oh, well, this was the run ID, 38 Bravo Echo Alpha yada yada. And inside there, I have a predictions.csv. Well, this is, if I look at, let's look at edit. This is my output. These are my input features. And then over at the end, I have a 0 or a 1 to reconcile whether or not we expect that they actually will owe money to the city of Chicago, or if they have paid it off or got the ticket dropped. So that's our output. That is our scored prediction that we can run through that score file, the deploy score file. That deploy score file is still running in our particular case, but it'll eventually finish up. We'll eventually be able to see it, and we'll get some results that look suspiciously similar to the ones that I showed off here from August 4th of 2023, because the files are still there. So we can see cluster is spinning up another node. If I go to compute and compute clusters, we can see that it's resizing. It's saying, I've already got a training job running, and I'm going to add another server for this scoring job. So I can have multiple data scientists submitting jobs here. And because each one only needs one server, I could have up to 4 of these running on the same CPU cluster without having to worry too much about waiting in line. Sorry, you gotta wait for everything to finish. Like right now, we're in the training phase. This training phase is going to take a little while. So it's going to finish up well after the presentation's over, because we're pretty close to the end of the presentation. So we've seen a lot of code. Are there any questions about that? I know that I blazed through pretty fast, and I will give you a link at the end where you can grab the code. You can try it out on your own. YouTube videos where you can see it in action a little bit slower paced. But if you have questions, get them in chat. Happy to answer. So building these pipelines in code. We built out this Azure ML pipeline. We created a Python script runner that was deploy train.py or deploy score.py. We created a bunch of YAML files. We created Python files for different steps in the pipeline. We did model training and testing. We saw that in the train.py file. We registered in register.py, and we wrote code to perform model inference and scoring. And actually, I didn't show you the scoring file, so let me briefly show you that. We have the script score model.py, and we don't have a config file in here. Score model.py has two required functions. So this is requirement for Azure ML. We need an init function and a run function. Init is how we build out the model. It is a global. I understand globals are ugly. I agree globals are ugly, but this is kind of the norm for Azure ML. In the init function, we create our model, we load it up, we instantiate it. So I'm going to get the context of our current run, build out Chicago parking tickets code first as the model name, go get the model from this path, and load that model using scikit-learn. We're going to then have a run function. So the init function runs once when the endpoint is called. The run function can run repeatedly, and we send in mini batches. Each mini batch is up to, in our case, 10 files. So mini batch is something that's configurable. It's configurable within the context of this deploy score. And we have mini batch size, and our deployment is 10. So that's how we figured out it's up to 10 files. So if I have 25 files in that directory, in that data set folder, I would have 3 mini batches, one with 10, one with 10, one with 5. And then what we're going to do is for each file, let's just read it as a CSV, and we're going to concatenate all of those files together. So this is a one-liner to do the for each loop that I had earlier. But this one, just a lambda to read the CSVs, map those all to concat, and generate one big data frame that has all of the records. And we're going to predict on all of those files and rows in there. We're going to create a new data frame with the prediction results, so pred. Specifically, the column payment is outstanding, and return data.assign payment is outstanding equals pred payment is outstanding. So basically, take our input data set and add on one new column, payment is outstanding. And that's our output. So that's what we do for scoring. Scoring here is a lot easier than the training process because I kind of cheated and my input files are already in the format that I need for training and testing. So I already dropped the columns I did not need. I already performed whatever processing I needed to do, added in time of day, license plate origin, vehicle type. If I needed to do all of that stuff, in the scoring, I would create a pipeline, have the same type of replace missing values, feature engineering, feature selection. I would have all of those different steps and then score. For the sake of simplicity, I wanted to have scoring just be very simple and said, once we've done all the training work, we can talk to our data engineers to just get the data in the appropriate format. So yeah, that was our building pipelines in code. We did model training and testing, we registered, we performed scoring, and I did the demos for that. So let's talk very briefly about MLOps, machine learning operations. In the software engineering world, over the past couple of decades, we've seen automation of code deployment become a critical thing. In Azure ML, we're seeing something similar. We see in the data science world a similar process. They're like 15 years behind, but certainly we're seeing the same steps. Model deployment manually via the Azure ML Studio UI. And then you say, man, I hate clicking so much. Model deployment using manually run notebooks. So I don't have to click as much, but I got to be awake when it's time to redeploy. Model deployment using the Azure CLI or the SDK like we did. A lot fewer clicks. That was just, what was our model deployment? It was running a Python script saying Python deployed to train.py. That was our model deployment process. Yeah, there's many fewer clicks, but still manual. And then we get to model CI/CD using a tool like Azure DevOps or GitHub Actions. And that's where we get to more sophistication of, well, when the code changes, perform retraining. Or when we get new training data, perform retraining. Or if the data sets drift over time, perform retraining. Machine learning operations, it's built off of these principles of DevOps, but it's also tailored to a world where it's not just code that's important, but also your data and your machine learning artifacts, your trained models, your weights. These are just as important as the code, and we need to be able to store them. We need to be able to work with them. We need to be able to update them and verify them and compare them across time. So the biggest problem here isn't necessarily deployment. It's redeployment, retraining, and evaluating over time. A proper treatment of MLOps would take an entire session, which is true because I've created an entire session for it. So, all right, over the course of this talk, over the last almost 2 hours, we've been here for quite some time, we've looked at different ways to take Azure Machine Learning from I'm going to perform drag and drop in a UI to writing code, whether in notebooks or in Python scripts or other languages. We could also do this in R or C# or F#, Java, whatever. We've introduced MLflow. We've introduced the Azure Machine Learning analogs to MLflow, and we've seen how MLOps can really help us push out these changes more efficiently. If you want to learn more, I'm going to give you the link to where you can grab the slides, where you can grab the demos, where you can grab links to additional resources. And as a matter of fact, I'm just going to go to it right now, give you an idea of what you're going to see. What you're going to see on here, and I do this for all of my talks. I've got my abstract, I've got my slides, which is what we just went through, demo code, which is a GitHub repository. I've got links to additional resources, a whole bunch of resources here. I also have additional media. Apparently I haven't created the additional media for this one, which is a shame. But let's go to the next talk in the series, which, by the way, next talk in the series, Practical MLOps with GitHub and Azure ML. In that one, additional media, I have a playlist for Azure ML videos. So here's my playlist. These are, whoa, I don't want to hear myself talking. Okay, there we go. I have, what is this? 16 videos in the Azure ML series. So if you're interested, starting from the very basics of here's Azure ML up to code first programming, this stuff that we talked about today. So 4 different videos on that, and then getting into MLOps, GitHub Actions, using DVC, and integrating Azure ML and Power BI. So there's a whole lot of stuff we did not cover. Got videos on that. You can check all that stuff out. If you have any questions afterwards, please do feel free to email me, or if you have any, if you want to hit me up on X, I got that available. If you want to throw money my way for consulting, you can reach out to me there. I don't do as much consulting as I used to, but I am still available for that kind of stuff. So with that, I want to say thank you all so much. Hope you enjoyed the talk. And if you do have any questions right now, get them in chat, and we will certainly answer them away. In the meantime, while I'm waiting to see if there are any questions, that is going to wrap up our Triangle Area SQL Server user group meetings for the month. Hey, thank you. By the way, welcome in. Let me double check. We do have one more episode of Shop Talk that's coming up on the 29th. So on Monday, Shop Talk, basically the Triangle Area SQL Server user groups board members get together and we talk about whatever topics come up that day. So the next user group meeting will be the second Tuesday of February, Advanced DBA group, third Tuesday, main meeting, fourth Tuesday, Business Intelligence, Data Science. So, all right, looks like no major questions in chat. This will also be posted up on our YouTube channel in a couple of days. And I think we're going to wrap things up for tonight. So thank you all for coming out. Thank you all for watching. Hope you enjoy it. And until we see each other in a future Triangle Area SQL Server user group meeting, everyone, Take care.